Let's see one more example on second normal form. Given the relation cat flower, this is the entire table given, and FDs are given like this. Then we are supposed to decompose into second normal form. So first of all, find out what is the candidate key. Now let's see what are all the attributes that are covered in the right side of the functional dependencies. If there is an attribute which is not present in the right side, then that should definitely be present in the candidate key. Okay. Now if you check it, in the right side, C is there, E and F are there, G and H are there, I and J are there, and only A, B and D are not there in the right hand side. Therefore, every candidate key is supposed to contain A, B, D, right? Now let's check whether ABD is enough or not. See, ABD are necessary to be present in any candidate key. Now I want to check whether ABD is enough or not. So if I find out ABD plus, if I find out the closure of ABD, then I am going to get from the first functional dependency, I am going to write ABD first. Now from the first functional dependency, AD is there on the left side, and here also AD is there. Therefore I can include its right hand side, which means C. And again BD is there on the left side, and BD is here as well, so I can include E and F, right? And again AD is there on the left side of the third functional dependency, and AD is here, therefore I can include its right hand side, so which is GH, right? And the last one, and this one is A is there in the left side, and A is here, therefore I can include I, and H is there on the left side, isn't it, of this FD, and H is there here, so I can include J. So I can include all of them. So what can I say? ABD is a candidate key. Now if you try to delete anything from this, it will not be a candidate key because they are definitely not there in the right side of any FD. Now if I try to add anything, that will become redundant, which means that is not required. If I try to add anything, that will become a super key. Therefore ABD is the only candidate key possible. Now based on this candidate key, you can find out the partial dependencies. If the part of this candidate key is determining any non-key, then you can say that it is a partial dependency, right? So if you see this part of it, so this is definitely partial dependency. Why? Part of this key AB is determining C, which is a non-key, and it is also a partial dependency because part of the key ABD is determining the non-key, right? F. And also this is also partial dependency because AD is part of the key determining GH. It is also partial dependency because A is a part of the key determining I. And if you see the last one, this is not partial dependency, but it is called as transitive dependency. We shall deal with it later. As of now, we don't want to look at it, right? So only thing that I am worried about is whether this is a partial dependency or not. It is not a partial dependency. So for now, we don't have any problem with it. Got it? So all the other partial dependencies, I have to find the closures of the left hand side, and I have to decompose the tables that way. Now what about AB plus? Why am I finding out AB plus? Because this is a partial dependency and I want to decompose the table, right? So with AB I want to take away all the attributes that are determined by it. Now if I find out AB plus, I am going to get AB, and because of AB I am going to get C. That's it, I guess. Okay, only ABC, and because of A here I'll get I as well. Okay, and now BD plus. So if I try to find BD plus, I am going to get BD, and because of BD I am going to get EC, EF. That's it, right? And now I have to find AD plus. So if I find out AD plus, I am going to get AD, and because of AD I am going to get GH, and because of A I am going to get I, and because of H I am going to get J. These are all the attributes I am going to get. And again A is also a partial dependency, and if I write A plus, I am going to get AI. So this is one way of trying to decompose it. Now if you see ABCD, the entire table ABCD, EF, G, H, I, J. Now I am going to decompose it this way, right? So because of AB I am going to get ABCI. So ABCI, I am going to make a new table with AB as the key there. Why? Because that is what is present in the left side of that functional dependency. And now for the newly formed table ABCI, AB can be the candidate key. That is why I am writing like this. ABCI is a new table with AB as the candidate key, right? And the second table is because of BD plus, I am going to get BD EF, and for the newly formed table BD can be the candidate key because BD plus is getting all this, right? And then because of AD I can write ADGHIJ, and for the newly formed table AD is the candidate key, right? And again because of A I am going to get AI, and I is the candidate key for the newly formed table, right? And now let's see what are all covered. CI is covered somewhere, and EF is also covered somewhere, and GHIJ are covered. Therefore everything is covered other than ABD, and anyway you are going to maintain a new table or a separate table containing the original candidate key. The reason you maintain this is whenever you are trying to merge, we'll always merge through this, right? See, for example, if you want to merge this table and this table, because if you get a query about what is the value of I for a given F, something like that, then if you want to merge these two, there is no intersection between them. Therefore you have to merge it first with this one, either this one and this one, and the result you merge it with this, or you merge this one and this one, and the result you merge with this, right? So because of maintaining this entire decomposition will become lossless. Got it? So you can merge any two tables through this one. Check it. If you want to merge these two, I think you can merge them directly because A is the common attribute and A is the key for this. If you want to merge these two, you are going to merge through this one, right? ABD. And if you want to merge this one and let's say this one, the intersection is A is not a key for both of them, and also I is not a key for both of them, therefore you have to go through this. Got it? So by maintaining this, we are making the entire decomposition lossless. Okay. Now let's try to see whether the resulting tables are in second normal form or not. How can I check it? Just see what are the functional dependencies applicable on each table, and let's find out whether they are fully dependent or partial dependent. Now on the first one you can write AB determines C and then A determines I, only that. On the second one I can write BD determines EF, and on the third one I can write AD determines GH and A determines I, and on this one I can write A determines I, and on the third one, that's it, right? So how many functional dependencies? All the 5 functional dependencies, you can see them here. Therefore you need not test whether this set is covering that set. Exactly both the sets are same. In case if something is missing, then you might have to test whether this set is covering that set or not. Got it? Okay. Now check this. So is there any partial dependency in each table? So is this table in second normal form or not? Now if you observe this table is containing AB is the key, and if you see this is fully functional dependent. C is fully functionally dependent on AD, but I is partially dependent on part of the key, right? So this is partial dependency. Why? Key is AB for this table, and A determines I is part of the key is determining a non-key. Therefore there is again partial dependency. So what you should do? Decompose it, right? So let's decompose this one into two tables in such a way that A, B, C. See how to decompose it? Find out A plus. If I find out A plus, I will get AI. Therefore AI will go into the other table, and A, B, C will remain in one table. For this table A will be the candidate key, and for this table AB will remain as the candidate key. Now functional dependencies will be AB determines C and A determines I. Now if you see this, now this after new decomposition, you are going to see that this one is second normal form. The reason is AB is the candidate key and left side is full candidate key. Therefore it is not a partial dependency. This one is in second normal form because A is the candidate key and A determines I is not the partial dependency. Got it? Therefore these two tables are in second normal form. And if you check this, BD is the candidate key and left side is full candidate key. There is no partial dependency, and therefore this is in second normal form. And if you check this is not in second normal form because AD is the candidate key for this table, and A determines I is a partial dependency, and so again divide it. So I divide it in such a way that A, D, G, H, J, this will be in one table and AI will be in the other table. Find out A plus and you write there. Got it? And now if you check it, AD determines GH will be applicable here, right? I think one more H determines J is also applicable here, right? And let us put H determines J here, and again A determines I here. Now if you observe this, H determines J is not a partial dependency, it is another dependency. We are not worried about it now. Now if you see this, AD is the candidate key and left side is a candidate key, therefore it is not a partial dependency. And here also H determines J is not a partial key because it is not, H is not a part of the key. Got it? Therefore this one is in second normal form and this one is also in second normal form. Got it? And this one is also in second normal form. There is only one. See, whenever the candidate key contains only one attribute, then the table will always be in second normal form. What is the reason? Because there is nothing called as part of the key there. Therefore there will nothing be called partial dependency. Whenever the candidate key is containing more than one attribute, then if a part of that candidate key is determining some non-key, then only you are getting this issue, right? But if you don't have more than one attribute there, then there is nothing called part of it. Got it? Therefore any table with only one attribute in the candidate key is always in second normal form. Got it? And if all the attributes are all the attributes are key attributes, which means ABD is the key here, all the attributes are key attributes, there is nothing called non-key attribute. Therefore this is also in second normal form always. Why? Because partial dependency is part of a key determining non-key. If there is no non-key at all, then there is no problem at all, isn't it? Therefore this is in second normal form. So all these are in second normal form after this decomposition. Therefore after decomposing, how many tables I got? 1, 2, 3, this one is already counted, 4, 5, right? So after decomposing this, now after decomposing this table into 5 tables, how many? 1, 2, 3, 4, 5. All the 5 tables are in second normal form and all the dependencies are preserved. You can check this. All the dependencies are preserved and it is lossless, because in every step I have seen that whenever I decompose, I am always maintaining a common attribute which is the primary key for one of the tables. Therefore the decomposition is lossless, FD preserving, and the tables are all in second normal form. Okay, fine.